A massive envelope of gas is stretching from Andromeda's core. It extends over 1 million light-years toward us. This halo has already reached halfway to our own galaxy. We thought we knew our closest galactic neighbor, but it turns out that we were very wrong about it. The galaxy you can see with your naked eye is just the beginning. Recent discoveries reveal Andromeda is twice as large as we imagined. It contains 1 trillion suns, a staggering number, and it may not even collide with us after all. Look up on a clear autumn night to see it. Find the constellation Cassiopeia, shaped like a W. Move your eyes slightly toward the constellation Perseus. You might be able to see a faint, fuzzy smudge. That faint smudge is the Andromeda Galaxy. But here is what nobody ever tells you about it. What you are seeing with your own eyes is a lie. The visible part, that gentle blur of light, spans about 3 degrees. That is 6 times wider than the full moon in the sky. It is already massive and already impossible to fully grasp. But scientists using NASA's Hubble Space Telescope discovered something that changes everything we thought we knew. Andromeda does not end where the faint light fades away. It just keeps on going and going and going. In 2015, astronomers measured something previously invisible. They measured a vast halo surrounding the galaxy. It is not made of stars or planets, but of gas, hot diffused plasma stretching outward from the galaxy. It is like an invisible ocean surrounding the stellar island. This discovery came from a project called AMEGA. This stands for Absorption Map of Ionized Gas in Andromeda. The team used 43 quasars as background lights. Quasars are the brightest objects in the entire universe. They are powered by supermassive black holes billions of light-years away. As their light traveled toward us, Andromeda's halo absorbed it. It absorbed specific wavelengths of the quasar light. Each dip in the brightness of the quasars revealed the halo's extent. The measurements that they made were absolutely staggering. This vast halo stretches 1.3 million light-years from the center. In some directions, it reaches as far as 2 million light-years. If human eyes could see this gas, Andromeda would be huge. It would appear roughly 3 times the width of the Big Dipper. It would completely dominate the entire night sky, the biggest feature you would ever witness every single night. It would be an inescapable and awe-inspiring sight. This confirmed halo contains a great deal of mass, at least as much mass as half of all the stars in the galaxy. Think about that for a moment and what it means. 1 trillion stars are burning brightly in Andromeda's disk. The halo matches half of that mass in pure invisible gas. This is not just empty space between the galaxies. This is the galaxy's own atmosphere, its breathing room. It is the material that it uses to create new stars. It does this over billions of years of cosmic time. But there is something that the scientists did not expect. Something that changes our entire relationship with this neighbor. The halo of Andromeda reaches halfway to the Milky Way. Our own galaxy most likely has a similar gaseous envelope. The math of the situation is simple and also terrifying. 1.3 million light-years from Andromeda's core. 1.3 million light-years from our own galaxy's core. The two galaxies are 2.5 million light-years apart. The halos of the two galaxies are already touching each other. What we thought was a future collision has already begun. 2.5 million light-years separates us from Andromeda. Let me try to translate that distance into something more familiar. 1 light-year is equal to roughly 6 trillion miles. If you multiply that by 2.5 million, you get a huge number. You get 15 quintillion miles, a truly vast distance. 15 followed by 18 zeros, an almost unimaginable number. At highway speed, driving day and night without stopping, you would need 44 trillion years to finally arrive there. Yet, in cosmic terms, Andromeda is practically right next door. It sits in what astronomers call the local group of galaxies. This is a collection of roughly 100 known galaxies. They are all bound together by the force of gravity. The Milky Way and Andromeda are the two largest members. Everything else in the local group orbits around them. They orbit like planets around two massive twin stars. Between us and Andromeda lies mostly nothingness. This is intergalactic space, the vast and empty void. The density in this space drops to less than 1 atom per cubic meter. For comparison, Earth's atmosphere at sea level is much denser. It contains about 25 quintillion molecules per cubic meter. The space between the galaxies is the closest thing to true emptiness, the closest thing that exists anywhere in the universe. Light is able to cross this void for 2.5 million years. It does so without hitting anything substantial along the way. There are no planets, no asteroids, and no clouds of gas. There are just occasional stray stars that have been ejected from their home galaxies, wandering forever in the dark. But our recent discoveries have revealed the void is not quite empty. Those vast halos we just discussed fill the space with thin plasma. The temperature in these halos reaches hundreds of thousands of degrees. Yet the gas is so incredibly sparse and diffuse. You could pass right through it without feeling anything at all. This material comes from both of our galaxies. When stars explode as supernovas, they blast heavy elements. Elements like iron, carbon, oxygen, and silicon. These are the fundamental building blocks of planets and of life. Some of that material is able to escape the galaxy entirely. It drifts outward, cooling and spreading as it goes. This process forms the vast halo that surrounds the galaxy. Scientists have confirmed something remarkable by studying this halo. They have discovered that it is layered in its structure. Two nested shells of gas are surrounding the Andromeda Galaxy. The inner shell contains different elements and temperatures, different from the outer shell that surrounds it. This complex structure tells a fascinating story. The galaxy has been feeding on its smaller neighbors for billions of years. Each of these cosmic meals has added new material to the halo. Each merger has stirred the halo like cream swirling in coffee. The layers that we see are like scars from these ancient collisions. And buried deep in this halo are clues about what is coming next. The gas that is located between us and Andromeda is not static. It is moving, flowing, and responding to the gravitational pull, the pull of both of these massive galaxies. Think of two large whirlpools that are slowly spiraling toward each other. The water between them begins to churn long before they touch. The halos of our two galaxies are already interacting, but the visible parts of the galaxies have not noticed this yet. The great collision has already started in a way, not with a loud bang, and not with stars crashing together. It began quietly and invisibly with the mixing of gas. Project Amiga's findings have revolutionized our understanding. They were published in 2015 and updated through 2025. Using Hubble's Cosmic Origins spectrograph, the team mapped the halo. They mapped it in a level of detail that was unprecedented. They measured not just its immense size, but also its composition. The halo contains huge amounts of what are known as heavy elements. Oxygen, carbon, nitrogen, silicon, and sulfur are all present. All of these elements were forged deep inside of stars. They were then ejected during the violent deaths of those stars. Over Andromeda's long lifetime, a lot of material has been expelled. Nearly half of all the heavy elements that have been created by its stars. They have been expelled beyond the visible disk of the galaxy. The galaxy has essentially been bleeding metal into space. It has been doing this for many billions of years. This enriched gas spreads outward at hundreds of miles per second. Some of it is able to escape from the galaxy forever. Some of it eventually falls back onto the galaxy. It is then recycled into new generations of stars. This is how galaxies are able to breathe over cosmic time. But here is the most critical discovery from the project. Andromeda's vast halo extends 1.3 million light-years in our direction. The Milky Way is sitting 2.5 million light-years away. Since the Milky Way and Andromeda are similar in size and type, scientists assume that our own galaxy has a comparable halo. The math of the situation becomes completely unavoidable. Both of the halos extend roughly 1.3 million light-years. When you add those two numbers together, you get 2.6 million light-years. This means that they must be overlapping with each other. We cannot easily study the Milky Way's halo from our position inside it. It is like trying to understand the shape of a forest. Trying to do so while you are standing among all the trees. Everything around you is blocking your view of the whole. But by studying the Andromeda Galaxy, we are looking at our own future. These two massive galaxies are like cosmic twins. They have a similar mass, a similar structure, and a similar history. What is true for one of them is likely to be true for the other. The overlap zone between the two halos represents something unprecedented. It is two galactic halos that are mixing together for the first time. Their gases are interacting on scales that we can barely measure. This interaction is very subtle at this point in time. The densities of the gas are so incredibly low, nothing dramatic is happening between them just yet. But the force of gravity never ever stops working. Every single particle of gas in both of the halos feels the pull of both of the massive galaxies. Over many millions of years, this pull will grow stronger. Think of it as being like two soap bubbles floating toward each other, long before their thin films actually touch each other. The air currents that are flowing between them begin to shift. Forces that we cannot see are preparing for the inevitable moment. The moment of contact between the two of them. The bubbles do not realize that they are doomed to collide. They just continue to drift closer and closer to each other. The fact that the halos are touching means the merger is not a future event. It is happening right now as we speak all around us. We are living inside the opening act of a great cosmic collision. A collision that will take billions of years to finally complete. But how fast is Andromeda actually moving toward us? And what will happen when the solid parts finally meet Andromeda is known to dwarf the Milky Way in its size. For many decades, scientists believed that the opposite was true. They thought that our own galaxy was the larger of the two. They thought it was more massive, had more stars, and was more dominant. New measurements have completely shattered that old assumption. The visible disk of the Andromeda Galaxy spans a huge distance. It is roughly 200,000 light-years across. The Milky Way, in comparison, measures about 100,000 light-years. Andromeda is therefore about twice as wide as our own galaxy. But that comparison only includes the bright disk where most stars live. When you factor in the full extent, including the halo, Andromeda's true diameter reaches 2 million light-years. It is a true monster of a galaxy, a cosmic giant. This galaxy contains approximately 1 trillion individual stars. The Milky Way, on the other hand, holds between 200 and 400 billion. Andromeda has at least twice as many suns as our galaxy. It might even have 3 times as many suns. Each of those stars could potentially host its own planets, and each of those planets might harbor its own moons. The sheer scale of the matter that is organized into one system. It is a system that is gravitationally bound, and it defies comprehension. NASA's Hubble Space Telescope captured a stunning image, the most detailed image of any external galaxy ever taken. The project was called the Panchromatic Hubble Andromeda Treasury. It required over 400 individual pointings of the telescope. 7,398 separate exposures were taken. They were taken from July 2010 through October 2013. The final mosaic image contains 1.5 billion pixels. It shows over 100 million individual stars in just a small section, a 61,000 light-year section of the galaxy's disk. 100 million stars in just one single photograph. And that is less than 1/3 of the entire galaxy. The resolution of the image is so extreme that you can see individual stars. You can see blue giants, red supergiants, and star clusters. You can see them embedded in the dark dust lanes of the galaxy. It is like photographing a vast beach from a great distance, and being able to resolve the individual grains of sand, except that this cosmic beach is larger than anything humans will ever visit. The stars that are visible in that incredible image are very far away. Their light has been traveling for 2.5 million years to reach us. When that light began its long journey through the void, early human ancestors were just learning to make stone tools on Earth. Andromeda's mass tells an even more dramatic story. For many years, astronomers had assumed it was more massive. They assumed it was 50% more massive than the Milky Way. Recent calculations using escape velocity have changed everything. As of 2019, Andromeda's total mass is now known. Its total mass, including dark matter, is about 0.8 trillion solar masses. The Milky Way surprisingly weighs 1.5 trillion solar masses. Our own galaxy is actually heavier than the Andromeda Galaxy, but Andromeda has more visible stars, more light, and more structure. This creates a puzzle for the astronomers to solve. Andromeda looks much bigger, but it actually weighs less. The answer to this puzzle lies in the distribution of dark matter. This is the invisible matter that makes up most of both galaxies. Our galaxy apparently has a more massive dark matter halo. Even though Andromeda's visible components are much larger, it is like comparing two massive icebergs in the ocean. One of them shows more of its bulk above the water, but the other one has a more massive hidden bulk beneath the surface. Yet even with all of these new measurements, both galaxies are still being studied, and the numbers that we have for them keep on changing. Imagine 1 trillion individual stars in a single galaxy. Not 100, not a million, but a full 1 trillion. It is a number so vast that if you counted one star per second, and you did this without ever sleeping, it would take you a long time. It would take you 31,700 years to finish. And these are not just dim dying embers of stars. Many of these stars are burning brighter and hotter than our own Sunday. Andromeda's stellar population spans the entire range of stellar life. Blue giants with temperatures over 30,000 degrees Celsius dominate the arms. These stellar monsters live fast and they die very young. They burn through all of their hydrogen fuel in just a few million years. Then they explode as brilliant and powerful supernovas. Then there are the yellow dwarfs, which are like our own Sunday. They are stable and very long-lived, burning for billions of years. The center of the galaxy glows with ancient red giants. These are stars that have already exhausted their core hydrogen. They have swelled up to become enormous in their size. Some of these red giants are large enough to swallow Earth's orbit. If they were placed at the Sun's position in our solar system, the spiral arms of the galaxy are themselves cosmic construction zones. Massive clouds of hydrogen gas are collapsing under their own gravity. The temperatures at the cores of these clouds reach 15 million degrees. At that point, nuclear fusion ignites and a new star is born. This process of star formation is happening constantly in the galaxy. Andromeda creates new stars at a rate of about 1 solar mass per year. That means every year enough gas collapses to form one new star, a star that is equivalent in mass to our own Sunday. Between all of the stars in the galaxy lies a great deal of dust. Hubble images show dark lanes threading through the bright spiral arms. These are not empty regions of space, but rather dense clouds of particles that are smaller than bacteria. They are made of silicon grains, carbon soot, and ice crystals. This dust absorbs the visible light, but it glows in infrared. NASA's Spitzer Space Telescope revealed the true extent of these structures. Long filaments of dust are spiraling inward toward the galaxy's center. Some of these filaments stretch for thousands of light years. The stars in the galaxy are not distributed evenly. The central bulge contains hundreds of billions of ancient stars. They are packed into a relatively small volume of space. The density of stars there is so high that the average distance is small. The average distance between stars is measured in light months. If the Earth orbited a star in Andromeda's core, the night sky would blaze with thousands of incredibly bright stars. You would never be able to experience true darkness. But here is what makes Andromeda's stellar population unique. The galaxy experienced a major merger 2 to 3 billion years ago. Two large galaxies collided with each other in a violent event. Their gas clouds slammed together at very high speeds. The impact triggered an enormous burst of star formation. For roughly 100 million years, the galaxy was a starburst. Andromeda created stars at 10 to 100 times its current rate. It became what astronomers call a luminous infrared galaxy. That ancient collision left permanent scars in the stellar population. You can see these scars in the age distribution of the stars. A huge number of the stars in the disk are about 2 billion years old. They all formed during that violent epoch when the merger peaked. These stars are now orbiting in very strange patterns. They are still carrying the momentum from their chaotic birth. All of those suns, all of that brilliant light and all of that history, and at the very center of it all, something hungry is waiting. The black hole at Andromeda's core is 110 million solar masses. It is compressed into a region smaller than our solar system. This object sits in the exact gravitational center of the galaxy. Everything else in the galaxy is orbiting around it. Unlike the black holes that power quasars, this one is quiet. It is an eerily quiet and underfed cosmic beast. Astronomers classify it as a low-luminosity active galactic nucleus. It emits very little radiation considering its enormous mass. The black hole at the center of the Milky Way is even quieter. Both of them are like cosmic hermits, barely eating. But being quiet does not mean that they are inactive. The Chandra X-ray Observatory has monitored Andromeda's core. It has been doing so continuously since 2009. These observations have revealed something completely unexpected. The black hole is known to flicker, but not like a light switch. It is more like a candle in a very drafty room. The X-ray output remains relatively constant for years, then suddenly it will spike in its brightness. In the year 2006, a bright flare erupted from the core. The brightness of the black hole increased dramatically. This elevated state of brightness lasted for several years. Then, in 2013, another bright flare burst from the core. Dr. Stephen Deal and his team at Michigan State University analyzed the data. They analyzed 15 years of Chandra data published in 2025. They tracked 4 different X-ray sources near the galaxy's center. One of these sources is located at the exact position of the black hole. The other 3 X-ray sources remain mysterious to us. By carefully separating the signals from these different sources, the team was able to create a complete light curve of the black hole. This showed how its brightness changed over a long period of time. The flares that they observed tell us that the black hole is eating. But the question is, what exactly is it eating? NASA's Spitzer Space Telescope was able to find the answer. Long spiral streams of dust and gas are flowing inward. They are flowing from thousands of light years away from the center. These filaments are following precise paths that are carved by gravity. They are spiraling closer and closer to the black hole. They are like water that is circling a drain. As the material approaches, the black hole friction heats it up. It heats the gas to millions of degrees, causing it to glow. The hot gas glows brightly in the X-ray part of the spectrum. When the feeding rate stays constant, the X-ray brightness also stays constant. When clumps of gas fall into the black hole, the brightness flares up. Recent research published in 2023 revealed how this feeding works. Computer simulations showed that a small disk of hot gas forms. It forms just outside of the black hole's event horizon. This disk is replenished by numerous streams from farther out. If the streams stay within certain size and flow rate limits, the black hole will remain in a relatively quiet state, but if you feed it too much too fast, it will react violently. The radiation output from the black hole would skyrocket. Strong winds would blow the gas away from the center. Star formation in the surrounding region would shut down. Andromeda's black hole seems to feed itself very carefully. The streams that were detected by Spitzer fit within the constraints for a steady and stable accretion process. The black hole consumes about 1/10,000th of a solar mass per year. That sounds like a tiny amount, but over millions of years, it adds up. The temperature of the gas that is falling in surprised everyone. Most supermassive black holes heat their food to very high temperatures. Tens or hundreds of millions of degrees is common, but Andromeda's black hole's gas is only a few million degrees. This is cool by the standards of cosmic black holes. Something about this galaxy's feeding process is different, and scientists still do not fully understand why this is. Andromeda is like a cosmic crime scene with evidence everywhere. The galaxy that we see today is not the same galaxy that existed 5 billion years ago. Something very violent happened to it in its past. Something that left permanent marks on its stellar population. Between 2 and 3 billion years ago, a massive merger occurred. This has been confirmed through multiple different studies. Two large galaxies collided with each other in a dramatic event. One of them was the original Andromeda Galaxy. The other was roughly 1/4 of its mass. The smaller galaxy plunged into the larger one at high speed. Their dark matter halos overlapped with each other first. Then their vast gas clouds crashed together at hundreds of miles per second. Powerful shock waves rippled through both of the galaxies. The impact compressed the gas to densities that triggered star formation. For approximately 100 million years, the galaxy was a starburst. Andromeda blazed as a luminous infrared galaxy during this time. Star formation peaked at rates 10 to 100 times higher than today. Thousands of massive new stars were being born every single year. The galaxy glowed with the combined light of hundreds of billions of young stars. If any civilizations existed in either galaxy at that time, their skies would have been dominated by spectacular star-forming regions, and they would have seen frequent supernova explosions. The evidence for this ancient merger comes from multiple sources. First, there is the age-velocity dispersion relation of the stars. The stars in Andromeda do not move the way they should, not if the galaxy had evolved peacefully over time. The older stars are orbiting much faster than expected. The younger stars are showing very strange velocity patterns. This anomaly only makes sense if a large population of stars was stirred violently by a merger about 2 billion years ago. Second, there is the star formation history of the galaxy. Astronomers can determine when stars formed by measuring their spectra. They compare the spectra to our stellar evolution models. A huge spike in star formation appears around 2 billion years ago. Far more stars formed during that period than in the billions of years before or after. Third, there is the structure of the galaxy itself. Computer simulations by multiple research teams have shown something. A merger with a mass ratio of approximately 4:1 explains Andromeda. It perfectly explains its current appearance in the sky. The models are able to reproduce the extended thick disk. They also reproduce the young thin disk and the prominent bulge. They can even reproduce the strange ring-like features that are visible. The merger also explains the giant stellar stream arc, an arc that is visible in the outer halo of the galaxy. That stream of stars is the leftover debris from the merger. It is the shredded remains of the smaller galaxy. It was torn apart by the powerful tidal forces of the event. The collision also injected enormous amounts of heavy elements. It injected them into the vast halo of the galaxy. Supernovas from the burst of star formation blasted these metals. They blasted iron, oxygen, and other metals out into space. Over Andromeda's lifetime, this process has expelled nearly half of all heavy elements. The halo that we discussed earlier is so enriched because of this violence. But Andromeda did not just stop there in its cannibalism. It is currently in the process of devouring its companion galaxy. The galaxy known as M32 is its current victim. M32 was once a normal spiral galaxy like our own. Now it is a compact, elliptical galaxy that has been stripped. It has been cannibalized by its much larger neighbor. Most of its outer stars have been stolen by Andromeda's gravity. This destructive process is still ongoing even today. M32 is shrinking every single million years. Galaxies are not the peaceful islands that they appear to be. They are cosmic battlefields where smaller victims are consumed by the larger predators that are in their neighborhood. If you look at Andromeda in ultraviolet light, it is different. The visible spiral arms that we are used to seeing disappear. In their place, something very strange and unexpected emerges. We see multiple concentric rings of young, hot stars. These rings are encircling the very core of the galaxy. These features should not exist in a normal spiral galaxy. NASA's Galaxy Evolution Explorer, or GALEX, captured stunning images. Stunning ultraviolet images that revealed the true extent of these rings. They glow with a brilliant blue-white color in the images. Each of these rings contains neighborhoods of massive stars. Their temperatures exceed 30,000 degrees Celsius. These stars are extremely young by any cosmic standards. They are just a few 100 million years old, mere infants. They are infants compared to the galaxy's age of 10 billion years. The rings are clear evidence of a past collision. When Andromeda merged with another galaxy 2 billion years ago, the impact of that collision sent ripples through the disk. Imagine dropping a small stone into a pool of still water. Waves of energy spread outward in concentric circles. In a galaxy, these waves are known as density waves. They compress the gas in the disk as they pass through it. The compressed gas then collapses under its own gravity. New stars then form in ring patterns following the wave. But there is another possible interpretation for these rings. Some researchers have proposed that the rings came from a different event, an event that happened about 200 million years ago. Andromeda may have collided directly with its smaller companion, its companion galaxy known as M32. Computer simulations using Spitzer data suggest this could be the case. This encounter could explain the ring structure that we see. The collision would have been a glancing blow, not a full merger. It would have been just enough to disturb the gas and trigger star formation. The star formation would have organized itself into the rings. The rings are clearest in the ultraviolet part of the spectrum. This is because that wavelength reveals the hottest and youngest stars. In visible light, the rings blend in with the spiral arms. In the infrared, they almost completely vanish from view. The dust lanes between the spiral arms show up starkly. They are stark against the bright rings when viewed in ultraviolet. These dark lanes are tracing the regions where star formation is happening. It is happening right now, at this very moment. Eventually, stellar winds from the newly born stars will blow the dust away. The lanes will then brighten with the light of the new stars, and the cycle will continue on and on over time. One particular ring structure in Andromeda stands out. It is a 10 kiloparsec ring that is about 33,000 light-years out. This ring contains enormous amounts of star-forming gas. Multiple studies have confirmed its existence through radio observations. The ring is rotating around the galaxy, but not as expected. Its orbit is tilted and eccentric, which points to a violent origin. The discovery of these rings has changed how astronomers understand galaxies. Spiral galaxies are not just slowly rotating disks of stars. They are dynamic systems that are shaped by violent collisions. Each major impact leaves behind fingerprints that can last for eons. Andromeda's rings are like fossils, evidence of past trauma, and astronomers know that at least 2 more major collisions are coming. One with the triangulum galaxy M33 is expected, and one with our own Milky Way galaxy is also possible. Each of these future impacts will create new rings. They will create new bursts of star formation and new cosmic scars. Scars that future astronomers might be able to study billions of years from now. If any astronomers are able to survive to see them. Andromeda is moving not just drifting but plunging toward us. It is moving at a speed of 68 miles per second. That is 245,000 miles per hour. That is fast enough to circle the Earth 10 times in 60 minutes. This velocity was first measured over 100 years ago. It was measured using the technique of spectroscopy. In 1912, astronomer Vesto Slipher used the Lowell Observatory. He used it to measure Andromeda's radial velocity. He found that it was approaching us at about 300 kilometers per second. That is equal to 186 miles per second. Later refinements of his measurements corrected this number. Current measurements using the Doppler effect place the approach velocity at roughly 110 kilometers per second. That is 68 miles per second, a very high speed. The blue shift in the galaxy's spectrum confirms its motion. It confirms that it is moving toward us, not away from us. Blue shift occurs when an object is moving toward you. The motion compresses the wavelengths of the light it emits. Blue light has shorter wavelengths than red light, so approaching objects appear slightly bluer than they actually are. The effect is very tiny for distant galaxies, but it is measurable. Modern spectrographs can measure wavelength shifts to extreme precision. The measurements that have been made are completely unambiguous. Andromeda is definitely coming right for us, but its velocity alone does not predict a direct collision. You also need to measure its sideways motion as well. Radial velocity tells you how fast something is approaching along your line of sight. Proper motion tells you how fast it is moving across the sky. If Andromeda has a significant proper motion, it might miss us. It could zip right past us like a car on an adjacent highway. If its proper motion is zero, we are directly in its path. For over a century, astronomers could not measure this proper motion. The galaxy is simply too far away to do so easily. Even at 2.5 million light-years, the angular movement is tiny. It is less than 1,000th of an arc-second per year. Earlier telescopes simply lacked the necessary precision. Then came the Hubble Space Telescope with its powerful vision. Between 2002 and 2010, Hubble repeatedly photographed Andromeda. It did not photograph the whole galaxy, but specific star fields. By comparing the positions of individual stars against a background of distant galaxies billions of light years away, astronomers were able to measure the tiny shifts in their positions. They averaged the measurements across thousands of stars. This was done to achieve a sub-pixel level of accuracy. The results of this study came out in 2012. Dr. Roland van der Marel led the team at the Space Telescope Science Institute. Their findings were definitive, and they were quite shocking. Andromeda's proper motion is consistent with zero. This is given the measurement uncertainties of the study. The galaxy is moving almost directly toward our own. The sideways component of its motion, if any, is too small to matter. A head-on collision between the two galaxies appeared to be inevitable. The announcement of this made headlines all over the world. Scientists created computer simulations showing what would happen. The galaxies would begin a series of close passes over billions of years. Each pass would distort both of the galaxies through tidal forces. Stars would be flung into new and different orbits. Gas clouds would collide and trigger massive bursts of star formation. Eventually, around 4 to 5 billion years from now, the two galaxies would merge completely into one. They would form one single giant elliptical galaxy. Astronomers even nicknamed this future galaxy Milkomeda, or some of them preferred the name Milkdromeda. For over a decade, this prediction stood completely unchallenged. Our textbooks declared that the collision was absolutely certain. Documentaries showed dramatic simulations of the merger. The merger became the established scientific consensus. Then, in the year 2025, everything changed. The Great Collision might not actually happen after all. New research published in June 2025 in the journal Nature Astronomy. It overturned decades of scientific certainty on this topic. Dr. Sawala from the University of Helsinki led an international team. They re-examined every single assumption that had been made. Their conclusion was that we have approximately a 50% chance of avoiding the merger entirely. 50-50, it is a cosmic coin flip for our galaxy's fate. Our galaxy's fate is hanging in a perfect and delicate balance. The team used the latest data from both Hubble and the Gaia spacecraft. Gaia has measured the positions and motions of over 1 billion stars. It has done so with an unprecedented level of precision. Combined with Hubble's measurements of Andromeda's stars, the team had the most comprehensive dataset ever assembled. But the data alone was not enough to make a final conclusion. They also needed to account for all of the uncertainties. Previous studies had assumed the most likely values for unknown quantities. Distance uncertainties, mass uncertainties, and velocity uncertainties. Each of these assumptions seemed reasonable on its own, but small errors can compound over time and become large. When you multiply many uncertain measurements together, the final uncertainty in the result can grow to be enormous. Sawala's team took a very different approach to the problem. They ran 100,000 different computer simulations. Each of the simulations varied the input parameters. It varied them within their known measurement uncertainties. Some of the runs assumed that Andromeda was slightly more massive. Others assumed that it was a little bit lighter. Some of the runs placed it closer to us, others farther away. The simulations also included the gravitational effects of other galaxies that are in our local group. This is where things started to get very interesting. Previous studies had treated Andromeda and the Milky Way as an isolated pair, two massive galaxies that were all alone in space. But the local group contains about 100 known galaxies. Most of them are tiny dwarf galaxies with just millions of stars. They are too small to matter much in this cosmic dance, but a few of them are substantial enough to affect the giants. The team focused on two of these smaller galaxies in particular, the Triangulum Galaxy, which is also known as M33, and the Large Magellanic Cloud, or the LMC. M33 is known to orbit the Andromeda Galaxy as a satellite. The Large Magellanic Cloud is known to orbit the Milky Way. Both of them are much smaller than their host galaxies, but both of them have enough mass to subtly alter the trajectories. They do this through their gravitational influence on the larger galaxies. Here is what the 100,000 simulations revealed. M33 actually increases the probability of a merger. Its gravitational pull tugs on the Andromeda Galaxy. It guides it slightly more toward the Milky Way over time. The effect of this is small, but it is measurable over billions of years. If M33 was the only other factor to consider, the collision would remain almost a certainty for us. But the Large Magellanic Cloud does the exact opposite. Its orbit around our galaxy runs perpendicular to the collision path. As it circles our galaxy, it is pulling us sideways. It is pulling us away from the path of Andromeda. It is not by much, but it is just enough to introduce some doubt. The Large Magellanic Cloud contains only about 15% of our galaxy's mass. That tiny fraction of mass is sufficient to change our fate. The simulations played out over 10 billion years of simulated time. In just over half of all of the runs that were performed, the two galaxies experienced an initial close pass. Their vast halos of gas interacted with each other. The encounter sapped a great deal of their orbital energy. Eventually, they would fall back together and merge into one. They would form a single giant elliptical galaxy, but in slightly less than half of all of the runs. The two galaxies swung past each other at a safe distance. They would then remain separate from each other forever. The probability of a merger is not exactly 50-50. The team calculated approximately a 50% chance of a merger that would happen within the next 10 billion years. There is only about a 2% chance of the collision happening in the previously predicted time frame of 4 to 5 billion years. Most of the merger scenarios now fall between 8 and 10 billion years in the future. This new discovery changes everything we thought we knew. It changes our understanding of our own cosmic neighborhood. The Large Magellanic Cloud looks like a faint smudge in the southern sky. It is a satellite galaxy that is orbiting the Milky Way. It is visible to the naked eye from the southern hemisphere. It contains roughly 30 billion individual stars in total. This is tiny compared to our galaxy's 300 billion stars. It is barely 15% of the total mass of the Milky Way. You would think that something so small would not matter much, but you would be completely wrong in that assumption. The Large Magellanic Cloud orbits perpendicular to the plane where the Andromeda Galaxy is approaching us. Imagine looking down at our own solar system from high above. The planets are all orbiting in a relatively flat disk. Now imagine a comet that is plunging toward the Sun from high above, almost straight down toward the plane of the solar system. The Large Magellanic Cloud's orbit is tilted just like that. It is tilted compared to Andromeda's approach vector. This particular orientation creates a very critical effect. As the Large Magellanic Cloud circles the Milky Way galaxy, its gravitational pull is tugging on our entire galaxy. Not forward or backward along the collision path, but sideways. The effect is like someone gently pushing on your shoulder, pushing while you are walking toward a doorway. One single small push does not change your direction much, but if there are continuous pushes over the course of an hour, you will eventually veer off of your original course. Sawala's team discovered that this sideways pull is enough. It is enough to reduce the probability of a direct collision. In the simulations that did not include the Large Magellanic Cloud, the merger rates climbed to above 70%. Including it in the simulations drops the rate to roughly 50%. One single small satellite galaxy is altering the fate of two giants. But the story of this cosmic dance gets even stranger. The Large Magellanic Cloud will not remain a satellite forever. The simulations show with near certainty that it will merge with us. It will spiral into the Milky Way within the next 2 billion years. Its orbit around our galaxy is slowly decaying over time. Each pass that it makes brings it closer and closer to us. Eventually, it will plunge into our own galactic disk. The collision between the two will be a catastrophic event. Their gas clouds will slam together at very high speeds. A massive burst of star formation will erupt across the impact zone. The merger will add 30 billion new stars to the Milky Way's population. This merger will also alter the Milky Way's motion through space. When the Large Magellanic Cloud finally falls into our galaxy, all of its momentum will be absorbed by our own galaxy. The impact of this will change our velocity and our trajectory. How this will affect the potential Andromeda collision is uncertain. The timing of all of these events is absolutely critical. If the Large Magellanic Cloud merges with us before Andromeda arrives, the sideways pull that it is exerting will simply vanish. Our trajectory through space will then change once again. This could push us back toward Andromeda or farther away. This depends on the exact details of the merger. The researchers admitted that even with 100,000 simulations, predicting 10 billion years into the future involves huge uncertainty. There are too many variables and too many small forces. These forces are accumulating over vast scales of time. They compared it to the process of weather forecasting. Meteorologists can predict tomorrow's weather with high confidence, but next week's weather becomes much more uncertain. Next month's weather is nearly impossible to predict, and as for next year, you can just forget about it. The chaos of interacting systems makes long-term prediction limited. Galaxies have even more complex interactions than weather systems. It is not just two objects that are orbiting each other. There are hundreds of different factors that are involved. The distribution of dark matter is one of them. Ongoing mergers with smaller dwarf galaxies is another. The gravitational influence of the entire local group is also a factor. Each of these factors introduces its own level of uncertainty. When you stack all of them together, the future becomes murky. Yet this new research reveals something very profound. The universe does not follow any predetermined scripts. Small objects can have the power to change the fate of giants. Tiny satellite galaxies can prevent apocalyptic collisions, or they can be the cause of them in the first place. The cosmic dance is more chaotic and beautiful than we imagined. Whether Andromeda collides with us or not, the LMC will. The Large Magellanic Cloud will definitely collide with us. That particular merger is coming for us in the future. The halos of the two galaxies are already merging right now. This is not just some kind of wild speculation. It is a confirmed fact that is based on real measurements. The question is not whether the halos are interacting. The question is, what happens next when they overlap? The physics of this process gets very complex. Both of the halos contain a great deal of hot plasma. The temperatures in this gas range from hundreds of thousands to millions of degrees. The gas is completely ionized, with atoms stripped of their electrons. This creates a charged soup of particles that responds to gravity. It also responds to pressure and to magnetic fields. As the halos begin to interpenetrate, several things happen. First, the gravity from both galaxies acts on the gas. The material in the overlap zone feels a pull from two directions. Some of the gas will eventually fall into the Andromeda Galaxy. Some of it will fall into our own Milky Way galaxy. The rest of it will remain suspended between the two. It will form a bridge of hot plasma that connects the two galaxies. Second, the pressure differences will create flows in the gas. Gas naturally moves from high-pressure regions to low-pressure regions. The halos are not uniform in their density and pressure. They are denser near the galactic centers and more diffuse at the edges. Where they overlap, the pressure gradients will drive circulation. Think of it as being like two large weather systems merging. The interaction creates powerful winds, turbulence, and complex flow patterns. These patterns will take many millions of years to play out. Third, the magnetic fields of the two galaxies will tangle together. Both of our galaxies have magnetic fields that thread through their halos. These fields are very weak, but they are organized over enormous volumes. When the halos of the two galaxies merge, the magnetic fields interact. They can amplify each other, or they can cancel each other out. They can also twist themselves into complex and tangled knots. Charged particles are known to follow magnetic field lines, so the geometry of the fields will determine where the gas flows. The observable effects of this halo merger are very subtle. You cannot see it in visible light with your own eyes. The gas is simply too hot and too sparse to glow brightly. But ultraviolet and X-ray telescopes can detect the signatures. Certain spectral lines appear when the hot gas absorbs light. It absorbs the light from distant background quasars. By comparing the absorption features from different sight lines, astronomers are able to map the density and temperature distribution of the gas. Project Omega did exactly this for the Andromeda Galaxy. They used 43 different quasars that are scattered behind it. Each of the quasars' light passes through a different path through the vast halo of the galaxy. By measuring the absorption in each of these spectra, the team was able to create a three-dimensional map of the halo. The map shows not just the extent of the halo, but also its internal structure. It shows the layering clumps and streams within the gas. Some regions of the halo are moving toward us. Other regions of the halo are moving away from us. The velocity structure of the halo reveals how the gas is flowing. Some of the flows are simple, following gravity toward the centers. Other flows are much more chaotic and turbulent. They have been stirred up by ancient collisions and mergers. The halo is not a static atmosphere around the galaxy. It is a dynamic and constantly evolving system of its own. As the Milky Way's halo and Andromeda's halo continue to interpenetrate, the combined system of the two will grow larger and more massive. It will also become hotter as the two gases mix. Eventually, if the galaxies do merge fully into one, the two halos will become one single enormous envelope. An envelope of gas surrounding the new merged galaxy. That combined halo would extend for several million light years. It would extend in all directions around the new galaxy. It would completely dominate the entire local group. Smaller satellite galaxies would be swimming through it like fish. But even if the two galaxies do not actually merge, even if they just pass each other and then separate, the halo interaction will leave behind permanent marks. Gas that is stripped from one galaxy will enrich the other. The heavy elements from both galaxies will mix together. The chemical composition of future stars will reflect this exchange. The merger of the halos is just the first act of the play. The merger of the stars will come much later. Milky is the name that has been given to the hypothetical merged galaxy, a galaxy that would result from an Andromeda and Milky Way collision. Some people prefer the name Milkdromeda instead. Neither of these names sounds particularly dignified for such an event, but the name is the least interesting thing about this potential future. If the merger does happen, computer simulations reveal the process. They reveal the step-by-step process of the merger. First contact will occur when the two galactic disks pass through each other. This is not a collision in the usual sense of the word. The stars are so far apart that individual stellar collisions are rare. They are virtually impossible to happen during the merger. The average distance between stars is about 100 billion miles. Even in the dense regions near the galactic centers, the stars still maintain a separation of billions of miles. When two galaxies merge, the stars pass between each other. They are like two clouds of gnats that are flying through each other. There are no direct impacts, just complicated gravitational interactions. But the gas clouds in the two galaxies do collide. Gas is much more continuous than the stars are. When two giant molecular clouds slam together at high speeds, powerful shock waves will compress the gas to extreme densities. The temperature of the gas will spike, and the pressure will skyrocket. Within millions of years, massive star formation will erupt. It will erupt across all of the collision zones between the galaxies. This is what is known as a starburst event in a galaxy. The merged galaxy would temporarily become a starburst galaxy. Millions of new stars would be forming every single year. The galaxy would blaze with the ultraviolet light of young, hot stars. This starburst would last for perhaps 100 million years. Then the gas reserves would be depleted and star formation would drop. It would drop back to its normal rates or even lower. Many of the massive stars that were born during the starburst would have died. They would have died as supernovas by that time. Their powerful explosions would have seeded the interstellar medium. They would have seeded it with a great deal of heavy elements. Future generations of stars would be more metal-rich. They would be more metal-rich because of this epoch. The final product, according to the simulations, would be an elliptical galaxy. It would not be a spiral galaxy like the two progenitors. Spiral galaxies require a great deal of organized rotation. They have disks of stars that are all orbiting in the same direction. When two spiral galaxies merge, the collision randomizes the orbits. The stars end up moving in all different directions. Some of them will be orbiting clockwise, some counterclockwise. Some will be plunging radially in and out of the center. This chaotic motion produces an elliptical shape for the galaxy, a football-shaped blob of stars with no distinct spiral arms. The merged galaxy would contain about 1.3 trillion stars. The combined population from both of the progenitor galaxies, it would span about 200,000 light-years across. This would be in its densest regions of stars. It would be larger if you were to count the extended halo. The total mass, including dark matter, would be huge. It would approach 2 trillion solar masses in total. This would make Milky one of the larger galaxies. One of the larger galaxies in the entire local group. It would not be a giant by cosmic standards, but it would be substantial. At the center of this new galaxy, 2 black holes would orbit. 2 supermassive black holes would be orbiting each other. The Milky Way's black hole is about 4 million solar masses. Andromeda's black hole is 110 million solar masses. Combined, they would create a binary black hole system, a system with 114 million solar masses. The two of them would spiral closer over tens of millions of years. They would be emitting powerful gravitational waves as they do so. Finally, they would merge into one single massive black hole. The collision would release more energy in gravitational waves, more energy than all the stars in the galaxy emit as light. The merged black hole would then settle at the new galaxy's center. Our own solar system would likely survive the merger. It would survive physically intact for the most part. The chances of another star passing close enough to disrupt orbits are low, but our location within the galaxy would definitely change. Simulations suggest a 50% probability of being flung out, flung 3 times farther from the galactic center, and there is a 12% chance of being ejected entirely, thrown into the vastness of intergalactic space forever. None of this matters for the future of our planet Earth. By the time any merger occurs, our planet will be uninhabitable. The sun is gradually brightening as it gets older. In about 1 billion years, the increased solar radiation will boil the oceans. All complex life on the Earth will come to an end. But the merger would be a spectacular sight to watch from somewhere else. Andromeda's center is a very strange and mysterious place. The galaxy has 2 bright nuclei, not just one. This double nucleus has puzzled astronomers since its discovery. It was discovered by the Hubble Space Telescope in 1991. The brighter of the 2 concentrations is designated P1. It sits offset from the true gravitational center of the galaxy. It contains mostly older and cooler stars, yellow and red giants, stars that have been shining for many billions of years. P1 appears as a compact and elliptical cluster of stars. It is very dense, with millions of stars packed into a small region. The dimmer concentration, which is called P2, sits at the actual center. This is where the supermassive black hole of the galaxy lives. P2 contains a strange population of stars for that region. Many of them are hot blue A-type stars which are young. These stars are just a few 100 million years old. Finding young stars so close to a supermassive black hole is unusual. The powerful tidal forces near a black hole should prevent star formation. Something must have created these stars despite the hostile environment. Within P2, there is an even more compact structure called P3. This is an embedded star cluster containing many young stars. They are orbiting the supermassive black hole in an eccentric disk. It is not a circular disk like you would normally expect. The orbits of these stars are very elongated and elliptical. The stars linger at the farthest point from the black hole. This creates a concentration of stars in one particular region. This eccentric distribution suggests a violent origin. One hypothesis proposes that the eccentric disk formed from a merger between 2 black holes in the distant past. If Andromeda's central black hole swallowed another black hole, the merger would have released enormous amounts of energy. This energy would have been in the form of gravitational waves. Those waves could have kicked the nearby stars into eccentric orbits. The pattern that we are seeing today would be the aftermath of that event. Another mystery is why P1 is offset from the center. When the double nucleus was first discovered, astronomers had a theory. They thought P1 might be the core of a small galaxy, a galaxy that Andromeda had recently cannibalized, a leftover nucleus that was falling toward the center. But this particular idea has some serious problems. Such a nucleus would have an extremely short lifetime. The tidal forces from the central black hole would rip it apart. It would do so within just a few million years. P1 has been there for a much longer period of time. The current understanding is that P1 is not a separate object. It is actually a part of Andromeda's own nucleus. The offset occurs because of the eccentric disk in P2. The disk's eccentricity creates an asymmetry in the mass distribution. This asymmetry shifts the apparent center of light away from the center. P1 is essentially a side effect of the weird stellar orbits in P2. Spectroscopic observations have confirmed that P1 has no black hole. The velocity distribution of the stars in P1 does not show the signature of a compact, massive object at its center. If P1 had its own black hole, the stars would orbit it at high speeds. But they do not. They are orbiting the galaxy as a whole. The double nucleus teaches us that galactic centers are complex. They are more complex than our simple models suggest. They are shaped by billions of years of mergers and interactions. The structures that we see today are like cosmic fossils. They are the remnants of violent events from the distant past. Every anomaly in a galaxy tells a story about its history. We are now learning to read those stories with our telescopes. Andromeda's nucleus will become even more complex when the Milky Way arrives. If the merger does happen, our galaxy's black hole will dive toward Andromeda's. The two of them will dance around each other for millions of years. They will do so before they finally coalesce into one. That merger will stir up the stellar population near both nuclei. It will create new eccentric orbits and new asymmetries. Perhaps future astronomers studying the merged galaxy will wonder. They will wonder what created such a strange configuration. They will be looking at the evidence of our own collision. Andromeda is not alone in the vastness of space. Two prominent companion galaxies are orbiting the giant spiral. These are M32 and M110. Both of them are what are known as satellite galaxies, and both of them are ultimately doomed to be destroyed. M32 is the brighter of the two companion galaxies. It is a compact elliptical galaxy that is sitting very close to Andromeda. It is only 190,000 light-years from Andromeda's center. That is closer than the edge of Andromeda's main disk. M32 contains a few billion individual stars. It appears as a small, bright blob when it is viewed through telescopes. It seems unremarkable and even forgettable at first glance. But M32 has a very tragic story to tell. This galaxy was once much larger than it is today. It was probably a normal spiral galaxy similar to the Milky Way. It orbited the Andromeda Galaxy at a safe distance for billions of years. Then something in its orbit changed over time. The orbital mechanics of the system brought it much closer. As M32 passed through Andromeda's outer regions, powerful tidal forces began to strip its stars away. The outer layers of M32 were torn off star by star. All of this material was stolen by Andromeda's much stronger gravity. This stripping process has taken billions of years to happen, and it is still happening right now, even as we watch. Each orbit that it makes brings M32 through Andromeda's disk. Each of these passages strips away more and more of its material. The galaxy is shrinking, and it is slowly dying. Eventually, nothing at all will remain of it except its dense core. That core might be able to survive as a globular cluster. It would be orbiting Andromeda forever as a small remnant, or it might be completely absorbed into the larger galaxy. It would be merged into the giant galaxy's stellar halo. The evidence of this cannibalization appears in Andromeda's outer structure. Long streams of stars are stretching through the halo. These are known as tidal tails, and they are long filaments of stars. Stars that were pulled from M32 during its close passages. Astronomers are able to trace these streams across vast distances. They follow curved paths that are shaped by the force of gravity. Each of these streams marks a different orbit from the past, a scar from an ancient passage of the smaller galaxy. M110 is sitting much farther out from the center. It is about 800,000 light-years from Andromeda's core. It is larger than M32, but it is much dimmer. It is a dwarf elliptical galaxy that contains several billion stars. M110 appears to be elongated and distorted. The tidal forces from Andromeda are stretching it like taffy. This galaxy is also in the process of being slowly devoured. Its ultimate fate has already been sealed by gravity. But Andromeda has more than just these two satellites. The Pan-Andromeda Archaeological Survey discovered dozens more, dozens of faint dwarf galaxies that are orbiting the giant. Most of them are extremely dim with just a few thousand stars each. They are so sparse that they appear more like loose clusters. These ultra-faint dwarfs are orbiting in the outer halo. They are protected by their distance, at least for now. Interestingly, many of Andromeda's satellites are orbiting in a disk. They are not scattered randomly in all directions. They are following a preferred plane around the larger galaxy. This suggests that they were all captured in a coherent group. Perhaps they all came from a larger galaxy that Andromeda destroyed. The fragments of this destroyed galaxy then became satellites. They are still orbiting in the same plane that they occupied. The distribution of these satellites tells us about dark matter. Each of these dwarf galaxies should have its own dark matter halo. By measuring how fast these satellites are orbiting, astronomers can infer the total mass of the Andromeda Galaxy. This includes its vast and invisible dark matter halo. The measurements consistently show that Andromeda's dark matter halo is huge. It extends at least 700,000 light-years and possibly over 1 million. The visible stars of the galaxy occupy just a tiny fraction of this. When the Milky Way and Andromeda eventually interact, whether they merge or not, their satellite galaxies will be thrown into chaos. Their orbits will change and some will be pulled from one galaxy to the other. Some of them will be flung out into intergalactic space. Some will fall into the galactic centers and be absorbed. The entire satellite system of both galaxies will be reshuffled. It will be like a deck of cards that has been shuffled. The large and small Magellanic Clouds will face uncertain futures. They are orbiting the Milky Way now, but Andromeda's gravity might capture them, or they might be ejected from the local group entirely. The same fate is awaiting all of Andromeda's satellites. It will be chaos and destruction for all the smaller galaxies. Galaxies that are caught between the two cosmic giants. NASA's Spitzer Space Telescope revealed something invisible to optical telescopes. Long filaments of dust are spiraling inward toward Andromeda's center. These are not just random clouds of dust and gas. They are highly organized and structured filaments. They are like rivers of material that are flowing toward the black hole, flowing like water that is spiraling down a drain. These filaments are stretching for thousands of light years. Some of them originate in the outer spiral arms of the galaxy. This is where the gas is still very abundant. Others are coming from the intermediate regions of the galaxy. All of them are following precise paths that are carved by gravity. The dust grains in these filaments are very tiny. They are smaller than bacteria, but there are trillions of them. Together they are able to absorb visible light. They then re-emit that light as infrared radiation. That is what the Spitzer Space Telescope is able to detect. Scientists have been able to trace these dust streams all the way to the very core of the galaxy itself. The paths that they follow are not straight lines. They curve and they twist following the gravitational potential. Think of a marble that is rolling toward the center of a funnel. It does not just fall straight down into the hole, it spirals inward following the slope of the funnel. These dust streams are doing the same thing on a galactic scale. This discovery was able to explain a long-standing mystery. How do the quiet supermassive black holes get fed? The active black holes, the ones that are powering quasars, they are consuming enormous amounts of material. Gas is falling into them very rapidly, and the accretion disk blazes. You can see these objects from across the entire universe, but the quiet black holes like the one in Andromeda barely glow, yet they must be eating something to produce any light at all. The answer is a steady and slow feeding process. The dust streams are delivering material to the central parsec. This is a region that is about 3 light-years from the black hole. There, the material forms a small hot disk of gas. This disk then feeds the black hole continuously, but the flow rate of the material stays very low. It is just enough to produce a faint X-ray emission. It is not enough to trigger any kind of violent activity. Computer simulations that were published in 2023 tested this idea. Researchers modeled how the gas behaves as it spirals inward. They found that if the streams stay within specific constraints, a stable feeding disk is able to form around the black hole. This disk does not flicker or burst in its brightness. It glows steadily, and the simulations match the observations. But here is the most critical detail of this process. The streams of gas and dust must be very narrow. If they are too wide, the material will fall in as clumps. It will not fall in as a steady and continuous flow. These clumps would cause the black hole to flare up. Its brightness would increase, then dim, then increase again. Andromeda's black hole shows very little variability most of the time. That means the streams that are feeding it must be just the right size. Spitzer's infrared observations were able to confirm this. The dust filaments are very narrow, just a few light-years wide. They are able to maintain this width even as they extend thousands of light-years. Somehow the galactic dynamics are organizing the flow. They are organizing it into these very narrow channels. The mechanism for this is not yet fully understood by us, but the observations that we have are very clear. Mixed in with all of the dust in these streams is gas. It is mostly hydrogen with some helium and trace amounts of heavier elements. The gas is following the same spiral paths as the dust. As the material gets closer and closer to the black hole, gravity is accelerating it to very high speeds. The speeds can reach thousands of miles per second. The friction between the layers of gas heats it up. It heats it to millions of degrees, causing it to emit X-rays. This feeding mechanism is known to differ from galaxy to galaxy. Some galaxies have massive reservoirs of gas in their centers. They are able to feed their black holes through different processes. Andromeda's method of using long dust streams seems to be optimized for a slow and steady accretion of material. It is elegant, efficient, and it keeps the galaxy's center calm. At least that is what happens for now for the most part. The black hole does not always stay so quiet, however. Sometimes it wakes up and becomes much more active. Bright flares are known to erupt from the center of the galaxy. The X-ray brightness of the black hole will spike, then it will slowly fade back to its baseline level. These events are telling us that the feeding process is not perfectly smooth. The Chandra X-ray Observatory has been watching Andromeda's nucleus. It has been watching since the year 2009. That is 15 years of continuous monitoring of the galaxy's core, the longest X-ray surveillance of any external galaxy's core. Dr. Stephen Deal and his team analyzed every single observation that was in the public archive. They constructed a complete light curve of the black hole. This showed how its brightness has changed over time. Most of the time, the X-ray output remains very stable. A baseline level of emission is coming from the hot gas. The count rates of the X-rays stay within a very narrow range. This confirms the steady feeding model for the black hole. Material is dribbling into it at a constant rate. The black hole is consuming it smoothly without any drama. But in the year 2006, something changed. The brightness of the black hole jumped up significantly. It was not a subtle increase, but a genuine flare event. The X-ray flux from the black hole doubled in brightness. Then it stayed elevated at this new higher level. The black hole remained in this high state for many years. Observations from 2009 through 2016 all showed this. They all showed an elevated brightness compared to earlier decades. Then, in the year 2013, another flare occurred. The brightness of the black hole spiked even higher than before. The event lasted for several months before it declined, but it did not return to the original baseline level. It settled at an intermediate level of brightness, higher than before 2006 but lower than the peak. There is a gap in the observations between 2016 and 2021. This makes the interpretation of the data more difficult. Chandra was not looking at Andromeda during those years. Budget constraints and scheduling conflicts meant other targets got priority. When the observations of Andromeda resumed in 2022, the black hole was still in an elevated state of brightness. Whether this is the tail end of the 2006 flare is unknown, or if it is the result of subsequent unseen flares. What is the cause of these bright flares from the black hole? The most likely explanation for them is clumpy accretion. Despite the narrow dust streams, the material does not flow with perfect uniformity. Small variations in the flow are known to occur. Maybe a molecular cloud in the spiral arms collapsed, and it sent a pulse of gas inward toward the center. Maybe the disk of gas inside the central parsec became unstable. Something must have disrupted the smooth feeding process. When extra material arrives at the black hole, the accretion rate increases. More gas spiraling in means more friction, more heating, and therefore more X-ray emission is produced. The flare represents the black hole gorging on a temporary surplus. Once the extra material has been consumed by the black hole, the brightness will return toward its normal baseline level. The team also measured something called the hardness ratio. This describes the balance between high-energy and low-energy X-rays. Hard X-rays have shorter wavelengths and higher energies. Soft X-rays have longer wavelengths and lower energies. The ratio of these two can reveal the temperature and density. The temperature and density of the emitting gas. Andromeda's hardness ratio is known to vary over time. During the flares, it shifts toward the harder X-rays. This suggests that the gas near the black hole gets hotter. It gets hotter during these feeding bursts of activity. The temperature can spike from a few million degrees to tens of millions. The exact values depend on the accretion rate and the geometry. Fast accretion is known to heat the gas more efficiently than slow accretion. Comparing these measurements to other galaxies provides some context. The Milky Way's supermassive black hole is even quieter than Andromeda's. It barely even flickers in its brightness at all. Other galaxies have wildly variable centers that are very active. Some of them can change their brightness by factors of 10 or more. They can do so within a matter of just a few months. Andromeda seems to fall somewhere in the middle of this range. It is mostly quiet, but it can be occasionally active. It is a moderate eater among the supermassive black holes. The flares are proof that the black hole is awake, not dormant. It is just being patient, waiting for its next meal to arrive. Imagine photographing a vast beach and resolving individual grains of sand. That is what the Hubble Space Telescope accomplished with Andromeda. The panchromatic Hubble Andromeda Treasury, or FAT, is a huge image. It is the most detailed image of any external galaxy ever created. The ambitious project began in the late part of 2011. It required over 1,000 Hubble orbits to complete. Each of these orbits lasts for about 90 minutes. This is as the telescope circles high above the Earth. During each orbit, Hubble spent precious minutes photographing Andromeda. It photographed a tiny section of the galaxy at a time. 411 separate telescope pointings were made, and 7,398 individual exposures were taken. The observations for the project spanned from July 2010 to October 2013. The logistics of this project were absolutely staggering. Hubble's field of view is tiny compared to Andromeda's size. It is like looking at a massive city through a drinking straw. To photograph a substantial portion of the galaxy's disk, astronomers had to create a massive mosaic of images. Each pointing of the telescope captured one small tile. The tiles were made to overlap slightly to ensure there were no gaps. Later, specialists at the Space Telescope Science Institute stitched them. They stitched all of the tiles together into one seamless image. The final mosaic image contains 1.5 billion pixels. When the full-resolution image was first released to the public, it was one of the largest astronomical images ever published. You can zoom in on the image almost endlessly. First, you see the entire galaxy in one view. Then you can zoom deeper, and the spiral arms resolve into star clusters. Deeper still, and the individual clusters separate into distinct stars. And even deeper, you can see the color differences between the stars. Blue giants, red giants, and yellow dwarfs are all individually visible. The image shows over 100 million individual stars, not galaxies, not clusters, but individual single stars. Each one of them is a sun that could be hosting its own planets. The section that was photographed spans 61,000 light years. That is more than half of the Milky Way's entire diameter. Yet it represents less than 1/3 of Andromeda's full extent. Scientists are using this image to study stellar populations. They are doing so in an unprecedented level of detail. They can measure the ages of the stars by their colors and brightnesses. Young blue stars are clustered in the spiral arms. This is where the star formation is currently the most active. Older yellow and red stars are filling the spaces between the arms. By mapping where different ages of stars appear in the galaxy, astronomers were able to reconstruct Andromeda's star formation history. They could see which regions of the galaxy had formed stars recently, and they could see which regions have been quiet for billions of years. The image also revealed thousands of different star clusters, globular clusters that contain hundreds of thousands of stars each, and open clusters with just a few thousand members. These clusters are the stellar nurseries of the galaxy. They are the places where gas clouds collapse to form many stars at once. Some of the clusters are billions of years old ancient relics from when the galaxy was very young and just forming. Others are just a few million years old cosmic babies. Dark dust lanes are threading their way through the bright regions. These are not empty voids, but rather dense molecular clouds. They are so thick with dust that they block the visible light. They block the light from the stars that are behind them. Within these dark lanes, new stars are forming right now. In the infrared wavelengths, these clouds glow with heat. The heat is from the embedded protostars within them. These are baby stars that are still surrounded by their birth material. The fat image represents more than just a beautiful photograph. It is a scientific gold mine for all of the astronomers. Researchers have published over 150 scientific papers using this data. Studies of stellar evolution, dust properties, and star cluster dynamics, spiral arm, structure the galaxy's rotation curve, and chemical composition. Each of these papers has extracted new understanding from the image. In January 2025, NASA released an updated mosaic. This version incorporated additional observations taken over the past decade. 600 total telescope pointings were included. The new mosaic captures 200 million individual stars. This is double the count of the original image. It also extends the coverage farther into the galaxy's outer regions, 200 million resolved stars in a single image. And that is still just a small fraction of Andromeda's trillion-star population. Most of the stars are too faint for even Hubble to detect. To detect at a distance of 2.5 million light-years. But the brightest of the stars, the giants and supergiants, they are shining as clear as daylight in the image. Each pixel of the image contains a story of its own. Each star has lived a unique and different history. Some of them were born during that massive merger 2 billion years ago. Others were formed more recently in collapsing gas clouds. Looking at this image is like looking at time itself. The light from these stars has been traveling for 2.5 million years. When it began its journey early, humans were just starting to walk upright. We are seeing Andromeda's distant past with our own eyes. but we are also looking at our own potential future. Andromeda spans 6 times the width of the full moon in our sky. If you could see its full extent with your naked eyes, it would completely dominate the autumn nights for you. But we cannot see it all as our eyes are not sensitive enough. We can only see the bright central core of the galaxy, a small fuzzy patch of light in the dark sky. It seems unimpressive unless you know what you are looking at. The apparent size versus the actual distance creates a paradox. The galaxy is 2.5 million light-years away. That is 15 quintillion miles of vast distance. Yet it appears to be very large in our sky. The reason for this is actually quite simple. Andromeda is genuinely and truly an enormous galaxy. Even at that vast distance, its physical size is huge. It translates to a significant angular size on the sky. Angular size is measured in units of degrees. A full circle contains 360 degrees. The moon in our sky spans about half of a degree. Your thumb, when held at arm's length, covers about 1 degree. Andromeda's visible disk extends roughly 3 degrees. That is 6 full moon diameters across the sky. In a dark sky with perfect conditions and adapted eyes, you can perceive the galaxy's elongated shape. It is not round like a planet, but stretched and elliptical. That is because we are viewing it at an angle, not face-on. If the entire gas halo of the galaxy were visible to us, Andromeda would span over 100 times the moon's diameter. It would stretch from the horizon to the horizon. The Big Dipper would be able to fit inside of it multiple times. Every single night, a quarter of the sky would be filled with the invisible presence of the Andromeda Galaxy. The thought of this is both beautiful and terrifying. But even without being able to see the entire halo, the visible portion is still very striking to see. Autumn and winter offer the best viewing from the northern hemisphere. The galaxy rises in the east during the evening hours. By midnight, it is passing almost directly overhead. This is for mid-northern latitudes in the world. By the dawn, it is setting in the west. Finding Andromeda in the night sky is easier than most people think. First, you need to locate the constellation of Cassiopeia. It is a W-shaped constellation in the northern sky. From the point of the W, you can draw an imaginary line, a line toward the constellation of Perseus. About halfway along that line, you will spot a faint smudge. That faint smudge is the Andromeda Galaxy itself. You do not need a telescope, just dark skies and some patience. Binoculars are able to transform the view of the galaxy. The central bulge brightens into a distinct core. The disk of the galaxy extends visibly on both sides. With a small telescope, you can even spot the 2 companion galaxies, M32 and M110, are visible. They appear as fuzzy spots near the main galaxy. Larger telescopes are able to reveal the dark dust lanes. They can also reveal hints of the spiral structure and brighter star clouds that are embedded in the disk. Photography is able to reveal even more of the galaxy. Long exposures can capture the light that human eyes cannot. The spiral arms of the galaxy emerge in these photos. Pink star-forming regions are glowing in hydrogen alpha emission. The full extent of the galaxy's disk becomes visible. Amateur astrophotographers are regularly capturing stunning images. They are doing so using their backyard equipment. Digital cameras and processing software have democratized this. The proximity of the galaxy is what makes this all possible. At 2.5 million light-years, it is still close enough for ground-based telescopes to resolve its structure. Galaxies at 100 million light-years are just smudges. Galaxies at 1 billion light-years are mere pinpoints. Andromeda is a giant that is looming in our neighborhood. It is close enough to be studied in great detail. It is close enough for us to feel a personal connection to it. That closeness also means we are invested in its fate. This is not some distant object that we will never interact with. This is our neighbor and our future dance partner. Whether the collision happens or not, Andromeda will shape our future. It will shape the evolution of the local group for billions of years. When you look at that faint smudge in the autumn sky, you are seeing across 2.5 million years of time. You are looking at light that left the galaxy before modern humans existed. The photons of that light traveled through empty space for all that time, just to be able to hit your eye and trigger a response. A response in your brain that makes you aware of something that is inconceivably distant yet somehow connected to our own cosmic story in a very intimate way. Andromeda is not just out there in the vastness of space. It is coming right here, right for us. Andromeda is bleeding metal out into the void of space. Not solid chunks of iron or copper, but individual atoms of heavy elements that were forged inside of stars, and then they were blasted outward by powerful supernovas. This process has been happening for many billions of years. The galaxy is slowly ejecting its own guts into the surrounding void. When massive stars exhaust all of their nuclear fuel, they will explode in a spectacular and violent event. The detonation releases more energy in just a few seconds, more than the star emitted during its entire lifetime. The temperatures during this event can reach billions of degrees. The pressures spike to values that do not exist anywhere else. Nowhere else in the universe except during these events. Under those extreme conditions, nuclear fusion does not stop. It does not stop at carbon and oxygen, but keeps on going. Silicon is fused into iron, and iron into nickel. The explosion can also create elements that are heavier than iron. It does this through a process called rapid neutron capture. Gold, silver, platinum, and uranium are all made this way. Every single atom of gold that is in the Earth's crust. It came from a supernova that happened long ago. Every silver ring and every platinum wedding band, they were forged in stellar explosions billions of years ago. They were then incorporated into the gas cloud that formed our solar system. The supernova ejector does not stay in the galactic disk. The explosion is so incredibly violent that the material escapes. It escapes at speeds of thousands of miles per second. This is faster than the galaxy's escape velocity in many regions. The material is able to punch right through the disk, and it keeps on going out into the halo and intergalactic space. Some of it is able to escape from the galaxy entirely. It is lost forever into the vastness of the cosmos. Over Andromeda's long lifetime, this process has expelled a lot. It has expelled nearly half of all the heavy elements its stars created. Half of all of them have been thrown away into space. The galaxy worked for billions of years to build those elements. It did so through the process of stellar nucleosynthesis, and then it just threw them all away into the void. This seems like a very wasteful process, but it is how galaxies evolve. The composition of the halo is what reveals this history. Project Omega did not just measure the extent of the halo, they also measured what the halo is made of, using spectroscopy on the light from background quasars. The team was able to identify absorption lines from specific elements. Oxygen, carbon, nitrogen, silicon, and sulfur were all present. They were present in the halo at measurable abundances. These elements are all called metals in astronomy. The term is a bit confusing because it includes non-metals. Non-metals like oxygen and carbon are included. In astronomical parlance, anything heavier than helium is a metal. Hydrogen and helium were created in the Big Bang. Everything else in the universe was formed inside of stars. So the presence of these metals in the halo is proof that enriched material has been ejected from the disk. The metallicity of the halo is not uniform, however. It is known to vary with the location within the halo. Regions that are closer to the galactic center show higher metal abundances. This makes sense, as the center has more stars in a smaller volume. More stars means more supernovas and more ejected material. The outer part of the halo is much less enriched with metals. The material there comes from stars in the disk's outer regions. This is where the stellar density is much lower, Supernovas are not the only enrichment mechanism. Stellar winds from massive stars also carry material into the halo. Red giants are known to shed their outer layers gradually. They do this over millions of years at the end of their lives. Planetary nebulas form when sun-like stars eject their envelopes. They do this at the very end of their lives. All of these processes contribute to the enrichment of the halo, but it is the supernovas that dominate the process. They are the most violent and the most efficient at launching material. The enriched halo of the galaxy will eventually fall back. Not all of the material is able to escape permanently. Some of the material will reach a maximum height and then slow down. It will eventually get pulled back by the force of gravity. This creates what is known as a galactic fountain. Gas is rising from the disk, cooling down, and then falling back. The entire cycle takes hundreds of millions of years to complete. Each of these cycles will mix the material in the galaxy. It will enrich the outer disk and spread the heavy elements. This is why the newer stars contain more metals than the older stars. The early generations of stars formed from nearly pure hydrogen and helium. They lived, died, and then enriched their surroundings. The next generation of stars incorporated those metals. They formed with a slightly higher metallicity. They lived, died, and then enriched the gas even further. This happened over and over, generation after generation. The metal content of the galaxy gradually increased over time. Our own Sun is a fairly metal-rich star by cosmic standards. It formed from material that had already been cycled through many previous generations of stars. The metals that are in our own bodies, like carbon and nitrogen, they were all forged in stars that died before the Sun existed. We are all made of recycled stardust from long ago. Andromeda's vast halo is filled with the very same stuff. It is the stardust that has been expelled from 1 trillion suns, and when the halos of our two galaxies finally merge, all of their metals will mix together in one big cloud. For many centuries, nobody knew what Andromeda was. It was just a fuzzy patch of light in the night sky. It was visible to the naked eye on clear and dark nights. The Persian astronomer Abd al-Rahman al-Sufi documented it. He did so in the year 964. He called it a little cloud in his writings, but he had no idea what he was actually looking at. As our telescopes improved over the centuries, the mystery deepened. Andromeda was found to show some kind of structure. It had spiral features, and it looked like swirling gas. Maybe it was a nebula inside of the Milky Way galaxy, a place where new stars were in the process of forming. Or perhaps it was a solar system that was under construction. Nobody at that time could have imagined the truth that it was an entirely separate galaxy, an island universe that was full of billions of stars. The idea seemed completely absurd to many people. By the early part of the 20th century, astronomers were split. They were split into two different and opposing camps. One group believed that the spiral nebulas, including Andromeda, were relatively nearby objects that were within our own galaxy. They were just clouds of gas, maybe a few thousand light-years away. The other group proposed something much more radical. Maybe these nebulas were not inside our galaxy at all. Maybe they were separate galaxies at enormous distances. On April 26, 1922, prominent astronomers had a debate. The Great Debate was held at the Smithsonian Museum in Washington. Harlow Shapley argued that the spiral nebulas were part of the Milky Way. Heber Curtis argued that they were external galaxies. The debate was focused on the observations and measurements of the time. Neither of the two sides was able to prove their case definitively. The data that they had was just not good enough yet. Shapley pointed to the Milky Way's apparent enormous size. Based on his studies of globular clusters, he made an estimate. He estimated that our galaxy was 300,000 light-years across. The spiral nebulas like Andromeda appeared to be too small. They were too small to be comparable galaxies to our own. They must be smaller objects that were within our own galaxy. His logic was sound given the assumptions that he made. Curtis countered with several different observations. First, the spiral nebulas showed dark dust lanes. These were similar to the ones seen in the Milky Way. This suggested that they were disk galaxies seen edge-on. Second, novae had been observed in the Andromeda Galaxy. These stellar explosions appeared to be much fainter than our own novae. If they were intrinsically similar, this meant Andromeda was far away. Third, Andromeda showed a very large Doppler shift in its light. It was moving at a speed of 300 kilometers per second. If it were inside of the Milky Way, such a high velocity seemed unlikely. The great debate ended without a clear and decisive winner. Both of the sides presented very compelling arguments. The question of the nature of the spiral nebulas remained unresolved. Astronomers would need much better measurements to settle it. Those better measurements came just a few years later. In 1922, an Estonian astronomer named Ernst Öpik used a new method. He measured the velocity of the stars within the Andromeda Galaxy. He did this using the technique of spectroscopy. The rotation velocity combined with the galaxy's apparent size. This allowed him to estimate the distance to the galaxy. He calculated a distance of 450 kiloparsecs. This is about 1.5 million light-years away, far beyond the boundaries of our own Milky Way galaxy. But Öpik's result was very controversial at the time. Many other astronomers did not trust his new method. They wanted more direct distance measurements to be made. Something definitive finally came in the year 1925. Edwin Hubble was using the 100-inch Hooker telescope at Mount Wilson. He photographed the Andromeda Galaxy repeatedly over time. He was able to identify Cepheid variable stars in the galaxy's disk. Cepheids are special stars that pulse in their brightness. They do so with very regular and predictable periods. The period of these pulses correlates directly with the star's intrinsic luminosity. This period-luminosity relationship had been discovered by Henrietta Leavitt. It provided a cosmic yardstick for measuring distances. You measure the period of the star, and then you can calculate its true brightness. You then compare that to its observed brightness in the sky. The difference between the two reveals the distance to the star. Hubble found Cepheids with periods that indicated they were very luminous. Yet they appeared to be incredibly faint in his photographs. The only possible explanation for this was an enormous distance. He calculated that Andromeda was roughly 900,000 light-years away. Later refinements of this measurement adjusted the distance. The distance is now known to be about 2.5 million light-years. But the conclusion of his work was very clear. Andromeda was a separate galaxy, a whole universe of stars, an island universe that was beyond our own Milky Way. The discovery completely revolutionized the field of astronomy. The universe was far larger than anyone had ever imagined. The Milky Way was not the entire cosmos, but just one galaxy among countless others in the vast universe. Andromeda was our nearest large neighbor in this infinite cosmic ocean. Heber Curtis had been right all along in the great debate. The spiral nebulas were indeed island universes. Andromeda is the most distant object that is visible to the unaided human eye. It is 2.5 million light-years away, or 15 quintillion miles. Yet, on a dark night away from the city lights, you can see it. You do not need any equipment, just your own two eyes. This creates a fascinating paradox for us to consider. How can something that is so far away be visible without technology? The answer to this reveals both Andromeda's enormous brightness and the inherent limitations of our own human vision. Andromeda contains a staggering 1 trillion individual stars. Their combined light output is roughly 260 billion times the Sun's. That is an incomprehensible amount of light being emitted. If you could collect all the photons that Andromeda emits, all the photons in all directions for just 1 single second, you would have more energy than humanity has used in its entire history. The galaxy is a true cosmic lighthouse shining brightly. but the great distance diminishes its apparent brightness. Light is known to spread out as it travels through space. It follows what is known as the inverse square law. If you double the distance, the brightness drops to 1/4. If you triple the distance, the brightness becomes 1/9. At 2.5 million light-years, the drop is astronomical. Each photon that Andromeda emits has only a tiny probability of eventually hitting the planet Earth. Yet enough of these photons are able to arrive here. Not many of them, but just enough to be seen. Andromeda's apparent magnitude is about 3.4. This is a logarithmic scale where lower numbers mean brighter objects, the faintest stars that are visible to the naked eye under perfect conditions. They have a magnitude of about 6.5. Andromeda is well above that particular threshold. It is one of only about 10 galaxies that are visible without a telescope. But here is the catch in this whole situation. Brightness alone does not guarantee the visibility of an object. The surface brightness of the object also matters a great deal. Andromeda spreads its light out across a large area, an area that is 6 times the diameter of the full moon. The same total amount of light when distributed over a large area. It appears to be much dimmer than if it were concentrated in a point. This is the reason why Andromeda appears as a faint smudge. It is not a brilliant and bright star in our night sky. If you could compress all of Andromeda's visible light into a single point, it would shine as a magnitude 3.4 star. It would be easily visible and bright enough to be noticed immediately, but it is spread out across 3 degrees of the sky. Each tiny patch of the galaxy contributes only a faint amount of light. Your eye struggles to be able to detect this faint glow. Human vision evolved to be able to detect contrast, the differences in brightness between adjacent regions. A star works very well for this, as it is a bright point. A bright point against a very dark background has high contrast. This makes it very easy for our eyes to see. But the Andromeda Galaxy has a very low contrast. The galaxy is glowing just slightly brighter than the surrounding sky. This is especially true near cities where there is light pollution. The light pollution raises the background brightness of the sky. In these conditions, the galaxy completely vanishes from view, not because it has gotten any dimmer, but because the contrast has dropped. It has dropped below the detection threshold of our eyes. This is why Andromeda is easier to see with your peripheral vision. The center of your retina, which is called the fovea, has mostly cone cells. These cells are responsible for color and fine detail, but they are not very sensitive. The surrounding part of your retina contains more rod cells. These cells are extremely sensitive to light, but they are colorblind. When you look slightly away from Andromeda in the sky, its faint light will hit your rods instead of your cones. Suddenly, the galaxy will appear to be much brighter and clearer. Astrophotographers are known to exploit this very effect. They use their peripheral vision to frame Andromeda through their cameras. Once it is centered, they will look away and then capture the image. The galaxy will appear far more prominent in their photos. It is not because their cameras are more sensitive than our eyes. It is because long exposures are able to accumulate light over time. Your eye is constantly resetting itself and cannot accumulate photons. A camera sensor can do this, however, which is why it works. The paradox of Andromeda's visibility is now resolved. It is visible because it is intrinsically very bright, but it is difficult to see because its light is spread so thin. The distance and surface brightness fight against its visibility. The intrinsic luminosity fights for its visibility. The balance between these two is very precarious. It is just barely visible under the most ideal of conditions. In truly dark locations away from any artificial light, people sometimes are able to notice Andromeda by accident. They will look up at the night sky and see an unfamiliar fuzzy patch, something that was not there before except that it was. They just had never noticed it there before. Human attention is naturally drawn to bright points of light. We tend to overlook the more diffuse and faint glows. Andromeda is hiding in plain sight in our night sky. 2.5 million light-years away from us. Visible to the naked eye, a galaxy containing 1 trillion suns, it is all reduced to a faint smudge that most people never see. The gas that is feeding Andromeda's black hole is cool. It is only a few million degrees Celsius in temperature. That sentence sounds completely insane on the surface. Millions of degrees being described as cool is strange, but in the context of supermassive black holes it is accurate. Most of the active black holes heat their accretion material to very high temperatures. They can heat it to tens or even hundreds of millions of degrees. Some of them are able to reach billions of degrees. The gas in these systems glows white-hot in the X-rays. These systems are visible from across the entire universe. Quasars are powered by black holes that are devouring huge amounts of matter. They are shining brighter than their entire host galaxies. They are true cosmic furnaces of incredible power. Andromeda's black hole is very different from these. When NASA's Chandra X-ray Observatory first imaged the core, it did so in the year 1999. Scientists at the time had expected very high temperatures around 50 to 100 million degrees. The standard models of black hole accretion had predicted this. Instead, they measured a temperature of just a few million degrees. This was cool by comparison to what they had expected. Dr. Michael Garcia and Dr. Stephen Murray announced the findings. They announced them in January of the year 2000. They had identified the central source of the X-rays. Its X-ray spectrum revealed the temperature of the gas. The low value of the temperature shocked everyone. Something was wrong with the standard models of black holes, or something about Andromeda's black hole was unique. To be clear, a few million degrees is still ridiculously hot. It is hot by any of our everyday standards. Iron is known to melt at about 1500 degrees Celsius. The surface of our own sun reaches 5500 degrees. Its core is able to hit 15 million degrees. Andromeda's black hole environment matches stellar core temperatures. The atoms there are completely ionized with their electrons stripped away. The matter exists as a plasma of pure energy and charged particles, but compared to typical supermassive black hole accretion, it is a relatively cool and calm environment. The question for the astronomers then became why? What is keeping the temperature of this gas down so low? Several different factors are known to contribute to this. First, there is the accretion rate of the black hole. Andromeda's black hole consumes very little material. It consumes about 1/10,000th of a solar mass per year. That is an incredibly slow rate of consumption. Less material falling into the black hole means less friction, and less friction means that there is less heating of the gas. The gas does not reach extreme temperatures because there is not enough of it to be colliding violently with itself. Second, there is the geometry of the feeding process. Remember those long dust streams that Spitzer discovered? They are delivering the material to the black hole very gradually. The gas is spiraling in slowly over many millions of years. It has plenty of time to radiate away some of its thermal energy. By the time that it reaches the inner accretion disk, it has already cooled down somewhat from its initial state. Third, there are the magnetic fields in the region. The region around the black hole is not empty space. Magnetic fields are threading their way through the plasma. These fields can tap into the rotational energy of the gas. They can convert it into other forms of radiation. This process is known as magnetic braking, and it removes energy. Lower energy in the gas means a lower temperature. The magnetic field is essentially providing a cooling mechanism. Fourth, there are the winds that are coming from the disk. Even the quiet black holes are known to produce outflows. The radiation pressure from the hot inner disk pushes some of the gas outward. This creates a powerful wind of particles and energy. This wind is carrying away both energy and material. The mass that remains in the disk is therefore depleted. This in turn helps to lower the temperature of the gas. All of these factors are combined together to keep the region cool, to keep Andromeda's central feeding zone relatively cool. But cool is a very relative term in this context. If you could magically transport yourself to that location, you would be vaporized in an instant by the conditions there. The intense radiation would tear you apart before the heat became an issue. Humans are evolved to survive at a temperature of 300 Kelvin. Andromeda's black hole environment is at millions of Kelvin. It is thousands of times hotter than anything in our solar system. The temperature is also known to vary during the flares. When extra material falls into the black hole, the heating increases. The temperatures can spike to tens of millions of degrees temporarily. The X-ray spectrum of the black hole also hardens during these events. More of the high-energy photons will appear in the spectrum. Then, as the flare begins to subside, the temperatures drop back down. Comparing Andromeda to our own Milky Way reveals some similarities. Our galaxy's central black hole, Sagittarius A star, also has cool accretion. It has the same few million-degree temperatures as Andromeda's. Both of our galaxies have quiet and underfed black holes. This is not just a coincidence, as similar galaxies produce similar centers, but not all of the galaxies in the universe are like this. Elliptical galaxies are known to often have much more active centers. They host much hotter black holes that are consuming material rapidly. The difference between them comes down to the gas supply. Spiral galaxies like Andromeda and the Milky Way have most of their gas locked up. It is locked up in their stars and in their disks. Very little of it remains to feed the central black hole. Elliptical galaxies are often the result of galaxy mergers. These mergers are known to stir up the gas in the galaxies. They provide a fresh supply of fuel for the black holes. The black holes then are able to feast on this new material. When Andromeda and the Milky Way eventually collide, if they do collide, their central black holes will get a boost. Fresh gas from the merger will flood inward toward the centers. The accretion rates of the black holes will skyrocket. The temperatures of the gas will soar to new heights. Both of the black holes will become much more active. They will heat their surrounding gas to hundreds of millions of degrees. The cool and quiet phase that they are in now will come to an end, so we should enjoy the quiet while it lasts for us. Earth's future in a merged galaxy would be very precarious. Computer simulations have predicted 3 possible outcomes for us. Most likely, nothing very dramatic would happen to our solar system. Our solar system would be able to survive the merger intact. The Sun would keep all of its planets in their orbits. Life would continue until the Sun dies naturally in about 5 billion years. But there is a twist to this particular story. The Sun's location within the new galaxy would probably change. The simulations show a 50% chance of being flung out, flung 3 times farther from the new galactic center. Currently, our Sun is sitting about 26,000 light-years from the core. In a merged galaxy, we might end up 78,000 light-years out. This would be in the outer suburbs of the new Milky. What would this change in location mean for us on Earth? Practically nothing at all for life on the planet. The Sun does not care where it is in the galaxy. Its process of nuclear fusion will continue regardless. The planetary orbits do not depend on the galactic position. The Earth would just keep on circling the Sun exactly as it does now. From a physical standpoint, nothing much would change for us, but the night sky would be transformed dramatically. Currently, the band of the Milky Way stretches across our sky. It is a river of stars that is visible on dark nights. That is our view as we look along the galactic disk. Billions of stars are too faint to be resolved individually, but they collectively glow as a milky band of light. From the outer reaches of Milky, the view would be different. The galactic center would appear to be more distant and dimmer. The band of stars would narrow and become less prominent. Instead of feeling surrounded by our galaxy, we would feel isolated. The stellar density in the outer regions is much lower. The space between the stars increases in these areas. Our nearest stellar neighbors might be twice as far away. Some stars would be closer, while others would be farther away. The rearrangement of the orbits during the merger would be random. But statistically, being farther from the center means lower density, fewer stars would be nearby, and the skies would be darker. But we would also have a clearer view of extragalactic space. With less intervening material, we could see distant galaxies more easily. The more disturbing scenario is a complete ejection from the galaxy. There is a 12% chance of this happening, which is not negligible. In those simulations, the solar system gets flung entirely out. It is thrown into the vastness of intergalactic space, orphaned. How does this kind of thing happen during a merger? Gravitational interactions during the close passes of the galaxies. As the stars from both galaxies intermingle with each other, they will affect each other's orbits through the force of gravity. Most of these interactions will be gentle with small velocity changes, but occasionally a star will pass through a dense region. It will do so at just the wrong angle to get a kick. It will get a gravitational kick, a kind of slingshot effect. If this kick is strong enough and is directed outward, the star will accelerate beyond the galaxy's escape velocity. It will then leave the galaxy forever with no turning back. The simulations suggest about 12% of the stars will suffer this fate. Roughly 150 billion stars will be ejected. They will be left to wander intergalactic space for all of eternity. If our sun becomes one of those ejected stars, the Earth's night sky would go nearly black. There would be no Milky Way band and no galaxy visible above. Just a few scattered points of light in the darkness. A few hundred stars would be within a reasonable distance, but most of the sky would be completely empty and void. The nearest large galaxy, whatever it might be, it would appear as just a tiny and faint smudge. We would be completely and utterly alone in the cosmos. Again, this would not affect life on the Earth physically. The sun would continue to shine and the Earth would continue to orbit, but psychologically it would be a devastating experience. Humans are comforted by the beautiful sight of the stars, the knowledge that we are a part of something much larger, part of a galaxy, a cosmic community of stars. An ejection from the galaxy would sever that connection. We would be adrift in the great cosmic ocean. The good news is that none of this really matters for humanity. By the time that any merger occurs, the Earth will be dead. The sun is gradually brightening as it gets older. In about 1 billion years, the increased solar radiation will be a problem. It will evaporate all of the Earth's oceans completely. The atmosphere will thicken with water vapor, creating a runaway greenhouse effect. The temperatures on the surface will soar to new heights. All complex life on the Earth will die out as a result. By 4 billion years from now, when the galaxies potentially collide, the Earth will be a scorched and lifeless rock. It might even be engulfed entirely if the sun swells into a red giant. The solar system's fate in a merged galaxy is irrelevant to us. We will not be here to be able to experience it. But for any future forms of life that might exist elsewhere, the ejection of 150 billion stars represents a massive diaspora, a scattering of solar systems across the vast cosmic void, isolated alone and drifting through the darkness forever. 2 supermassive black holes with a combined 114 million solar masses. They would be destined to merge into one single object. The collision would be the most violent event in the local group's history. It would be more energetic than all the supernovas in both galaxies combined. It would be more explosive than anything except the Big Bang itself. But the merger of the 2 black holes would not happen quickly. Black holes do not just simply crash into each other. First, they would orbit each other for many millions of years. They would be gradually spiraling closer as they emit gravitational waves. Those waves would carry away both energy and angular momentum. The orbit of the 2 black holes would then decay over time. The separation between them would begin to shrink. Initially, the black holes would be thousands of light years apart. Each of them would be orbiting in the merged galaxy's core. The Milky Way's 4 million solar mass black hole and Andromeda's 110 million solar mass giant. They would feel each other's gravity, but they would remain distant. Their interaction with the surrounding stars would dominate the dynamics. Stars that pass near either of the black holes would be flung away. They would be flung away at very high speeds in a slingshot effect. Each of these ejected stars would carry away some energy. That energy would come from the black hole's orbital motion. As the stars are slingshotted out, the black holes lose energy. They would then drift closer and closer together. This process is very slow and takes tens of millions of years. Eventually, the separation would drop to about 1 light year. At this point, the star scattering becomes much less effective. There would not be enough stars in the immediate vicinity. The black holes would then need a different mechanism to continue losing their energy. That is where the gas in the core comes into the picture. If enough gas remains in the merged galaxy's core, the two black holes will begin to interact with it. The gas friction will drag on the orbiting black holes. This process is known as dynamical friction, and it is very efficient. It is extremely efficient at very close ranges. The two black holes would be plowing through the gas. Each of their passages would create a wake of disturbed material. The drag from these wakes would sap their orbital energy. The separation between them would continue to shrink. From 1 light year down to 1/100th of a light year, the black holes would now be close enough to be a true binary, two black holes that are bound together by gravity. At separations below about 1/10th of a light year, gravitational wave emission becomes the dominant energy loss mechanism. The accelerating masses of the black holes generate ripples in spacetime. These ripples carry away a great deal of energy. The black holes lose that energy and spiral even closer. The orbital period at this stage might be just weeks or months. Two massive black holes whipping around each other once per month. The gravitational waves produced would be detectable from Earth. They would be detectable by space-based gravitational wave observatories. Future missions like LISA would be able to spot them. They would spot them years before the final merger. As the separation drops below 1 light day, the inspiral accelerates. The black holes would orbit each other multiple times per day. Then they would orbit multiple times per hour as they get closer. The gravitational wave frequency would increase and the signal would grow louder. Energy would be pouring out as space-time itself vibrates. Finally, the event horizons of the two black holes would touch. In less than a single second, the two black holes would coalesce. The combined mass would be slightly less than the sum of the originals. The difference in mass would be converted entirely to gravitational wave energy. About 10% of the total mass might be radiated away. That is over 10 million solar masses of energy released in gravitational waves during the final moments. For comparison, our Sun outputs about 2 solar masses of energy. It does so over its entire 10 billion year lifetime. This black hole merger would release 5 million times more energy. It would do so in under a single second of time. The space-time around the merger would shudder violently. Ripples would propagate out across the universe at the speed of light. The final merged black hole would be highly distorted. It would be spinning rapidly with its event horizon wobbling. Over the next few hours, it would settle down. It would emit additional gravitational waves as it rings down. It would ring down to a stable and final configuration. Then it would go quiet once again in the cosmos. A single, supermassive black hole at the center of Milky 114 million solar masses waiting for its next meal. This entire process from the initial orbit to the final merger, it takes between 10 and 20 million years according to simulations. This depends on the gas availability and the stellar density, but the end result of the process is certain. Two black holes cannot remain as a binary forever. Gravitational wave emission guarantees that they will eventually merge, unless the two galaxies do not collide in the first place. Then the two black holes will never meet each other. They will remain in their separate galaxies forever alone. Imagine standing on a rocky planet 4 billion years from now. Not on the Earth, as the Earth will be dead by then. The oceans will have boiled away and the atmosphere will be stripped, but somewhere else on a world orbiting a younger star. Farther from the galactic center and still habitable, you would look up and the sky would be in a state of chaos. Two massive galaxies would be interpenetrating each other. The Milky Way and Andromeda would be in the process of colliding. This would be their first close pass, not the final merger yet, but it would be close enough for some spectacular effects. The Andromeda Galaxy would be dominating half of the sky. It would no longer be a faint smudge, but a massive spiral. It would be stretching from the horizon to the horizon. Its individual spiral arms would be resolved and visible. Bright star clusters would be visible as glowing knots of light. The galaxy's core would be blazing like a second moon, except that it would not be reflected light from a star. It would be the combined luminosity of billions of stars, compressed into a small angular area of the sky. The band of the Milky Way would still be crossing the sky, but it would be distorted and warped by the interaction. The tidal forces from Andromeda would be pulling it, stretching it in some directions and compressing it in others. The band of the Milky Way would brighten as the stars are compressed. In other areas, it would thin out as the stars are drawn away. The familiar constellations of our night sky would be gone. They would be completely rearranged by the merger. The sun, if it still exists, would be sitting in a different region. A completely different region of the sky than it is today. New star-forming regions would be flaring up across both galaxies, where the gas clouds of the two galaxies collide. Shock compression would trigger massive bursts of star formation. These regions would be glowing a bright pink with hydrogen emission. Thousands of them would be scattered throughout both of the galaxies. The rate of star formation would be 100 times higher than normal. The two galaxies would be in the process of being transformed. Supernova explosions would be happening constantly in the sky. With so much rapid star formation, many massive stars would die quickly. The explosions would light up the night sky brightly. On average, several supernovas would be visible to the naked eye each year. Sometimes there would be multiple of them per month. Each one of them would be brighter than the planet Venus. Some would even be brighter than the full moon. They would fade over a period of weeks and then disappear. But new ones would be constantly replacing them. The sky would never be quiet during this time. Tidal streams of stars would be stretching between the two galaxies. Long arcs of stars that have been pulled from both systems. These streams would be glowing faintly like cosmic auroras, but they would be permanent structural features of the sky. They would be tracing the gravitational interaction between the two, visible evidence of the forces that are ripping both galaxies apart and pulling them together at the very same time. The combined view of this would be overwhelming and terrifying. It would also be incredibly beautiful to behold. Two galaxies worth of stars would be visible at once. Over 1 trillion suns would be shining in the night sky. The sky would never be truly dark during this period. Even without the sun, the starlight would illuminate the landscape. It would be a dim and ghostly light, but it would be present. Over the next few billion years, the galaxies would separate. They would swing past each other and then return for another pass. Each of these encounters would further distort both of their structures. The beautiful spiral arms would be shredded and destroyed. The stars would be flung into new and chaotic orbits. The organized rotation of both galaxies would become randomized. Chaotic motion would replace the orderly spiral patterns. Eventually, around 6 to 10 billion years from the first close pass, the two galaxies would have lost enough orbital energy to merge. They would fall together, interpenetrate fully, and become one. The sky would then be transformed once again for any observers. It would no longer be two distinct galaxies, but one giant elliptical blob. It would have less structure and be more uniform. But it would also be much brighter than the two originals. All of those stars would be mixing together in one big galaxy. The supermassive black holes would be sinking toward the center, They would be observable as a bright point of light, the active nucleus of the new merged galaxy. As gas falls into the binary black holes, they would produce radiation. They would produce intense radiation, maybe even a quasar, briefly illuminating the merged galaxy brighter than billions of stars. Then they would settle down and become quiet once again. Any far future civilizations, if any exist, would study the merger. They would analyze the spectra of the stars and track their populations. They would map the gravitational potential of the new galaxy. They would try to reconstruct what the original galaxies looked like, what they looked like before the Great Collision. This would be a form of archaeoastronomy, studying the past, reading the fossil record that is written in the stellar orbits and in the chemical abundances of the stars. They would discover that the two galaxies had approached each other for many billions of years before the merger, that their vast halos had touched long before their visible disks met, that their smaller satellite galaxies had been destroyed during the process. The large Magellanic Cloud would have been consumed by then. M32 would have been completely absorbed by Andromeda. All of them would have merged into the final product, and they would be looking outward toward other galaxies, wondering if any of them would merge with Milky Way in the future, wondering if the process of mergers ever actually ends, or if galaxies will continue to consume each other until only a few giants remain swimming in an empty universe, a universe that is growing ever emptier as dark energy pulls everything apart. The view from the Earth in 4 billion years does not exist. The Earth will not be there to see it happen, but the view from somewhere else will be absolutely spectacular, assuming that anyone is actually watching it happen, assuming that life is able to survive long enough to witness it, assuming that consciousness is able to persist across these vast timescales. Two massive galaxies that are in the process of colliding, 1 trillion stars that are rearranging themselves across millions of years. It will be the biggest show that the local group will ever produce. Whether anyone is watching it or not, it will happen. Gravity does not need to have an audience to work. It just acts relentlessly and inevitably until two become one. And Andromeda is already touching us right now,